All right. Good morning, and hope everybody's doing well. There is some interest on understanding a little bit more the calculations for the ballistic motion program that I had posted. And I wanted first to start with the program that we did, which was bouncing ball, in which the position of the ball was updated by just small increments, Vx and By. Why Vx and By? Well, because we look at the positions on the x and y plane, right? The Cartesian plane. So that means that you always have to tell the x and the y position for the point. So that means that there will be an increment on the x and an increment on the y. If you had done a little bit of, I guess, I don't know, at the end of Algebra 2, pre-calculus, somewhere in there, you do learn about vectors. So this would be, for example, our x and y, even though it's a point on the Cartesian plane, it could also be where a vector could start if the vector had a length. And that's what we're going to see now in projectile motion, in the ballistic motion. Let me close this one because we see over here that all we do is to change on the x and the y coordinates because there is no other factor affecting the position. But in ballistic motion, we do have different factors. If we were going to look at the actual physics behind it, the formulas are kind of a little bit too complicated for what we want to do in this particular class. But here it is. We have one with air resistance, even though it says that there shouldn't be, this. Somewhere in there is something with no dragging, but there is a drag force right here. And that's caused because of the air resistance. So the formulas are a little bit ugly for some of you. For some of you, probably is nothing more than, again, pre-calculus. So that's why the ones that is presented in the website are a little bit simpler. But you still want to understand what they mean. And so that's why I drew over here a vector in the actual trajectory of the ball. So the vector should be tangent to a point. So it's not really tangent right here. I did that on purpose so you could be seeing a little bit better. It could be more visible, otherwise it will hide in the actual curve over here. So this curve represents this particular input. I believe the velocity is 20 and the angle is 45. If you can see the parametric formulas right there over here. So again, the point of this vector will always depend on the x and y coordinates. The length of it, the magnitude of it, the absolute value of the vector is given by applying the, what is that called? You all know it, the Pythagorean Theorem, in which it will be vx squared plus y squared. That will give you the distance squared. So if I want to know the actual distance, I will do the square root of that. And that's what this first formula is right here. And the reason why you need that is because you need to know the point at every, you need to know, I'm sorry, not the point, you need to know the new velocity. The velocity changes. Let's see. So here we have everything that is on the right hand side right here is all the initial values. As you can see, it starts from the x and y are 0 right here at this point. So there is no, it's not thrown up from any, what I call it, height. So it starts from the origin of this Cartesian plane. And again, don't get too involved in the calculations, but I know some of you do want to know about this, and that's why I'm putting it over here. And you also want to know how this code is related to these formulas over here. So let's just make a little bit of sense without getting too involved in the details. You do know that if I do have velocity that's given, you want to know the components on the x and the y axis. So to know v of x is nothing more than applying v times the cosine of the angle. And in this case, for this particular example that you see over here, I use this one over here, the 45 degrees. To find out the v value on the y-axis, I did the same thing as the other one, but instead of cosine, I used the sine of that angle. Hopefully by now you all know that cosine and sine of 45 degrees, they're both exactly the same. The acceleration starts from 0 on both on the x and the y axis. And again, like in the bouncing ball, we didn't have any factors involved. It was like in small bags without air, without gravity affecting it. But here we do have both. Projectile motion or ballistic motion is related to those factors. So the initial velocity, we agreed that it was 20 and the angle was 45. So the time that it starts is 0. dt, what's dt? dt is, they call it here the time quantum. But for us, in terms of implementing this, we're just looking at how close do we want to draw the next point on the curve so we can actually see like a solid curve. When you draw it, if you remove this, the clear over here, and let's do that. I'm going to remove the clear. You will see that the curve is going to look pretty much the same as this one. Let me compile. I'm going to do this one over here, and I'm going to use 20 and 45 because the other one looks ugly, and I will tell you why that one looks ugly in a moment. So if we let this run, coming up soon. There we go. There you can see the same curve. The only difference between the two things is nothing more than the units. As you can see, I compressed the units over here so it can fit in my curve. I'm sorry, in my graph paper. But they're both actually the same. If I was going to change this x scale over here to be more like this one, it will look exactly the same. We'll look at this later. So actually, this is the challenge for you. It's actually drawing this curve as the ball moves. Over here, the ball is actually, this is actually the shadow of the ball, right? Because if you look at the actual code again, let's go back to the code. The circle is very tiny, so it looks like a curve instead of having, or the dots, the points on a curve, instead of having a ball. What I ask you to do is to have a ball there, not just the actual drawing of the curve. Okay, let's get back to the other values over here. So dt is how close do I want to draw the next point, which is 0.25. So the changes in the position are just very tiny, if you can think of it. And if you notice, the scale goes from 0 to max r. Max r is calculated over here, and that is based on the horizontal range, the maximum horizontal range. It works well for 20 and 45, but it looks very ugly for 180 and 60. And that's because this formula has been simplified a little bit, max R. If you test that one, you'll see that you will end up with a small graph and in the big canvas. So you could change that if you wanted to be more adaptable to the input. It's not necessary. I would suggest to use the right input so you don't have to manipulate so much code. Okay, let's go back down here because I know that that is where the interest is. So I hope you understand now what max R is. Mostly, and so the curve falls in the, or is drawn in the canvas. At it nice. It's appealing look. It doesn't care though about the max height, which I would have done that too, but I guess it's not that important either. It would not look, the canvas would not look square, it would look rectangular. And that's probably why they did it this way. So what's happening over here? Hopefully all of this, before you enter the while, it was clear to you, except that, did I talk about deceleration? Yes, at the floor, at the ground floor, there is no acceleration. You're against the earth, and we're going to say that there is no acceleration because we're about to throw the ball up. What else is in here? Anything else? No. Let's take a look. This means something for some of you probably, but it is also on the documentation, the comment, which is if y is the vertical axis, when y is 0 means that the ball hit the ground right here, or back on the ground. So both times, and you know that a parabola has two solutions, meaning crossing the x-axis. So here's one of them at 0, 0, and then the other one is right here. Do we care where it is on x? Well, the max R is what it is. But what we are calculating over here for the while loop is just to know that, make sure that y is greater than or equal to 0. If it is less than 0, that means that it already hit the ground and it's kind of going into the ground. We go back over here to this Pythagorean Theorem over here. So the increments or the changes in the position is based on the changes of x and the changes of y. And that's what we have over here. Take a look. I broke it up into Vx and Vy. So what's the velocity as a vector itself? Then we do the Pythagorean theorem. What about the acceleration? Well, once it's up in the air, we have over here some other factors that we didn't have at the bouncing ball. Here we consider in the air resistance, and right here also for the y, the air resistance, which is always, it's negative because it is, as it is resistant, and that's what is dragging it. Now, in terms of the x direction, the x-axis, it's not affected by any, the gravity only affects you vertically, right here, in this direction, right? So if I was going to draw G over here, G is pushing, is pulling down the ball. Let me see, can I draw? Let me see if I can draw that. If I can. Yeah. So technically, this will be straight down, vertical, and this will be G. Well, I'm going to draw actually a segment. And I can use it from here to here. And then let me eliminate this one over here. And so, oops, let me go back a little bit because I have both of them selected. Let me just select this one and now hide this one. There you go. So this represents gravity. G. I think that's good enough. I'm not going to make the arrow tip because it's a pain in the neck to draw an arrow tip with this software. All right, so in terms of the y component, we do have in the formula, we need another factor, g, the gravity. And it's 9.8 millimeters per second. I think it's somewhere in here. There we go. Here's the dragging force coefficient. Yes, I'm sorry, it's meters per second square. That's the gravity. And that's going to be changing the acceleration. This is going to be affecting the velocity. Take a look over here. Because the velocity, again, we look at it in terms of x and y. So the velocity a of x, as you can see over here, is only going to be affected by a constant, which is c. But here, ay is also affected by the gravity. So Vx and Vy will be changing. And if you looked at the video I show you, V of y is going to get smaller and smaller until it gets to 0 when it's at the top. And then it reverses direction. It's going to be pointing down because it's coming, the ball is actually coming down. First, it was going up. And so Vy was pointing up. And then coming in this direction, it's going to be pointing down. These are the formulas in the explanation of it, but I think they're more understandable to me on the actual code. But they're pretty much the same if you look at it. So the next thing would be, well, the latest velocity on the x component now is going to be changing by the acceleration on the x component times the actual amount of pixels that you want to move, or as they got it over here, time quantum. This is what's going to allow that to be drawn, because we're going to need this Vx, the change in Vx, because of the change in time, so we know what the new position is. And we always add into it, regardless where it is, we always add into it, even though sometimes these values are going to be negative. It will have to be negative at one point, because it's going to be coming down here. I did have to use the enable double buffering, so I don't have that flickering. So make sure that you do include that. It's not in the original program, the one that I gave you. I'm not sure why, but make sure you do type this in your program. Otherwise, you're going to have that flickering effect that looks pretty ugly. I think very soon I have a student or multiple students who will be posting their ballistic motion assignment. If you have any questions about any of the formulas that I explain, or you want to understand a little bit more, just message me or email me. I hope you're all doing well. I would like to have a Zoom meeting so we can see each other. Talk to you soon. Bye-bye.